Let's now talk about some properties, some definitions of matrices, transposition in particular, and some properties of these things, and well, a few other things. So the transpose of a matrix is the flip of a matrix. So as an example, suppose a matrix is A11 up to AMN, so there are M rows and N columns. The transpose, which is written as AT, T for transpose, will have N rows and M columns, and whatever the rows of the matrix now become columns of the matrix. So in particular, transposition converts row vectors to column vectors and vice versa. These are special cases. It's more general than that. For general rectangular matrices, you can define transposes. So these transposes will be important in some contexts. So this is one definition to do with transposes of matrices. And there are further properties of transposes. So the transpose of a transpose is the matrix itself. This should be clear even without looking at a formal proof, because if you flip the rows to become columns, and then you flip them again, so the new rows become columns, so therefore the columns become rows, right? When you're flipping rows to become columns, columns are becoming rows. So when you flip it again, then the rows will stay rows. So therefore, A transpose transpose is nothing but A. A plus B transpose is A transpose plus B transpose. If you want to prove this formally, you can think about, so A plus B transpose is Aij plus Bij transpose, which is Aj plus Bji, right? Which is nothing but Aj plus Bji, which is A transpose plus B transpose. So this is how you prove this formula, right? Some constant times A transpose, some constant times A, the whole transpose, is nothing but it's the same as the constant times the transpose of the matrix. Now here's a non-trivial property. AB times the transpose of AB is B transpose times A transpose. You'll be doing this one as an exercise. All right. So notice, by the way, in this case, AB transpose, the order of the matrices is in reverse order. So you have to be careful. Okay. Now let's look at some special matrices. So symmetric and skew-symmetric matrices. Symmetric matrices are those whose transpose are the same as the matrix themselves. So as an example, this is a symmetric matrix. This element is the same as this element, this one the same as this one the same as this one, right? And the diagonal elements remain the same when you transpose them. And you get the same element. A skew-symmetric matrix is a square matrix whose transpose is the negative of the matrix. So here's an example. 1 is the negative of -1. The -3 is the negative of 3, and -2 is the negative of 2. Therefore, this is skew-symmetric. So examples of where these matrices show up. So symmetric matrices, for example, are so suppose you want to ship from location I to location J. So if you want to ship from so this is location 1, 2, 3, 1, 2, 3. Then the cost of shipping from 1 to 2 would be maybe given by 120, and that would be also the cost of shipping from 2 to 1. Right? If shipping is just depends on distance, nothing else. Skew-symmetric things are more like vectors. When going from A to B is the negative, the cost of going from B to A. So that's a skew-symmetric matrix. Other examples of symmetric matrices, like bus station, costs of going from station A to station B. So this is NPR map. There's a property which we'll ask you to prove at some point. Any square matrix can be written as a sum of a symmetric matrix and a skew-symmetric matrix. So it requires proof, but it can be shown that M plus M transpose by 2 is a symmetric matrix, M minus M transpose by 2 is a skew-symmetric matrix. Triangular matrices are square matrices that have non-zero elements, square matrices that have non-zero element only on or above the diagonal, whereas lower triangular matrices are non-zero entries only on or below the main diagonal. So example, here's an upper triangular matrix, looks like a triangle, right? That's like an upper triangular matrix. This is an upper triangular matrix. This is a lower triangular matrix. This is also a lower triangular matrix. And these are, of course, the diagonal elements, right? The diagonal element matrices. These matrices will be important in solving linear equations. We'll see. Diagonal matrices, well, we already sort of said them, but diagonal matrices are those which are non-zero elements only along the diagonal. They have to be square. You can have non-zero elements only on the diagonal. They can have zero elements here as well. That would still be a diagonal matrix, but they cannot have non-zero elements not on the diagonal. Scalar matrix is something which is a diagonal element, which is a diagonal matrix, and all of the elements are equal. So, for example, 2, 2, 2, 0, 0, 0, 0, 0, 0. So this would be a scalar matrix. Okay? And these have an interesting property. That is, these matrices are indeed commutative. They commute with other matrices. So A times a scalar matrix is the same as a scalar matrix times A, which is the same as C times A. In particular, if I multiply this with A, it's going to be 2 times A. Now we can show that. Okay, because every element here is 2. In particular, scalar matrices whose elements in the diagonal are all 1 are very special. They're called unit matrices or identity matrices. So, for example, 1, 1, 1, 1. This is the 4 by 4 identity matrix. I'm trying this badly. Let's do this again. So, 4 by 4 identity matrix would have 4 elements on the diagonal, and then it would be something like this, right? Like this. In the future, for matrices like that, I'll just write it like large 0 here, large 0 here. This just means zeros everywhere here, zeros everywhere. And identity matrices are very special. So any matrix times an identity matrix is the same as identity matrix times any matrix is the same as the original matrix. Matrices behave like the number 1. Of course, matrices are not the same as numbers, but they be, in this case, identity matrices behave like the number 1. Let's look at some examples of matrices and matrix multiplication and where they're useful. So here's one example. Suppose a factory makes 2 types of computers, and it requires 3 types of ingredients to make a computer. And these are the amounts of costs making a computer. So the cost of raw components for this type of PC is 1.2 times 10,000. So let's see, $1.2 million for every 10,000 units. Okay? The cost of labor for this type of PC is $0.4 million for every 10,000 units. The second matrix B shows the numbers of millions of. Let's see. Oh, my mistake. These are the costs in thousands of dollars. These are the production figures in 10,000 units. Okay, so over here, this element is showing that in the first quarter of a year, the first type of computer, the cost was $30,000. Sorry, not the cost, the production figure. So 30,000 units were produced of the first type of computer, 60,000 units of the second type of computer. So overall, the cost of raw components, labor, and miscellaneous items in the 4 quarters can be computed by taking the matrix product of A times B. Because the matrix product, for example, when I do the matrix product of this times this, what am I doing? I'm basically taking, for the first PC, the cost of raw components times the number of PCs computed, plus the cost of raw components for the second type of PC times the number of PCs generated. And this, therefore, 13.2 is therefore the cost of raw components in the first quarter. Okay? So this is one compact way of computing the the costs for the company. Here's another use of matrix multiplication. So walking, let's say a person can do 3 types of activities. He can do walking, he can do bicycling, or he can do jogging. And the amount of calories that burns is 350, 500, and 950 calories for these 3 types of activities. And on these 4 days, he does these 4 different types of activities. So overall, the number of calories he burns are 825, 1325, 1000, and 2400. Right? And you can show this by matrix multiplication. Finally, suppose the here's another thing corresponding to transition matrices. So suppose in every 5 years, the number of commercial properties that stay commercial properties is 0.7, but commercial properties that become industrial properties is 0.2 fraction, and commercial properties that become residential is 0.1. Okay, so and similarly, the number of industrial that stay industrial is 0.9, and so on. Okay. So this matrix is sort of a transition matrix. It computes the transition probability every 5 years. So the question then is, given the fraction, given the number of units that were initially commercial, industrial, and residential, after 5 years, what fraction will be commercial, industrial, and residential? And using matrix multiplication, you can do that, and you can predict in the future as well. So these are 3 potential uses of matrix multiplication.